In this video, we'll talk about related rates problems, to what they are, how you can identify them, and how to think about going about solving these sorts of problems. So related rates are a new application we have for derivatives, and we'll see how this all plays out in a little bit. But we want to consider the following question. A spherical balloon is filled up with air at a rate of 4 cubic inches per second. How fast is the radius of the balloon increasing when the radius is 6 inches? The question is asking us about how fast the radius is increasing at a certain point, and we know something about the volume. The thing about this question, you might start writing down things you know. So we know how the volume of a sphere, or spherical balloon, relates to its radius, right? We know that the volume of the sphere is 4/3 pi r cubed with respect to the radius. And what else are we given in this problem? Well, we're given a radius of 6 inches. We easily find the volume there, but that's not what we really care about. We're looking at how fast is the radius of the balloon increasing. We know how fast air is being pumped into the balloon, and stuff from there. So the other fact we're told is this 4 cubic inches per second. So what is that? Well, that's the rate at which air is being pumped into the balloon, or particularly that's the rate at which the volume of the balloon is changing. That's how fast the size in terms of volume is growing. And so really, that's a derivative. That is the rate of change of volume. That is the derivative dv dt, where we're thinking the volume is a function of time, how fast it's growing over time. Now what the problem's asking us for is how fast is the radius changing. That really should be a dr dt. How fast is the radius changing with respect to time? And so I need to find some way to tie the rate of change of volume to the rate of change of the radius. I need to relate the rate of change of volume to that of the radius. Hence, these are called related rates problems. I want to relate one rate of change to another. I'm tying the rate of change of volume to the rate of change of radius, so that's a related rates problem. We're relating these two rates to each other. So what are related rates problems? The idea is what I mentioned before. The idea is I'm trying to connect one rate of change, i.e. one that I know, to another rate of change that I don't know. So in terms of this known and unknown rate of change, ideally I know an equation that connects this known quantity that I know about the rate of change for to this unknown quantity that I don't know the rate of change for. In this case, that was volume and radius. And we have the equation v equals 4/3 pi r cubed. And our goal is to take that equation and convert it to an equation that relates the different rates of change of these objects. And how do we make this happen? How do I go from something to its rate of change? That's a derivative. And the idea for this problem is basically, we want to view everything as a function of time, and then take a derivative in t, using whatever implicit techniques we need to take that derivative, and then see what happens. And this is one of the main points where Leibniz notation becomes really useful, because I don't want to take derivative in r, say for this volume equation up here. I want the derivative in t of that equation, and knowing that it's in t with writing dv dt and dr dt will make sure I know what I'm doing as I'm taking the derivative. That's the setup of these problems. That's how you can spot them. You spot them by noticing I want to take this rate of change and use it to find a second rate of change. That means it's a related rates problem. And then in the next video, we'll talk about how I actually go about solving these and working on the process for actually working out solutions to these sorts of problems.